We're going to be using these tables in order to determine the potentials of our voltaic cells. You may notice this little degree sign again. That is again for standard conditions because the exact voltage depends on the concentrations, temperature, and pressure, and so on. These reactions are reductions, and this is labeled up here for you that it's told these are cathode potentials or reduction potentials, either way you want to say that. But if it didn't say that, you should be able to tell that by looking at the reactions. Okay, it's not always stated which it is. It may just be given as potentials, and you've got to see which one it is. The way I can tell is because these reactions are reduction. Aluminum going from +3 to 0 is a reduction, and I should know that reduction occurs at the cathode. Okay, so these are right here, that symbol means reduction potential. And you can see we have a lot of values, some are positive and some are negative. The most favorable ones are positive and large. The larger, the more favorable. Well, the cathode is just one of the half cells, though. We'll have to also take into account the anode when we decide what the overall is. But it is true that this is the overall. If it comes out positive, then the reaction is spontaneous. And this value depends on both the reduction potential and the oxidation potential of the anode. These values are relative to this standard hydrogen electrode. It was just chosen kind of as the 0, and everything is compared against that. When we do these, we're more interested in the difference of the numbers, so it doesn't matter where that was changed or where that was 0 was defined. Also, these reactions are just simple metals exchanging electrons, most of them, and just know that on some charts you'll see a lot more complicated reactions involved with polyatomic ions and all kinds of things. But the table that I gave you has just the metals like this one, so we can focus on those. Okay, let's practice using the table. So again, I should be able to look at this and see that these are reduction reactions, and so these potentials are reduction potentials. And I'm comparing these two. I kind of have highlighted which are most easily reduced. Well, remember that favorable is positive, and the bigger, the more favorable. And so these, as I move down this chart, the numbers get bigger and more positive. So those are going to be more favorable. So down the chart is more favorable, and so the most easily reduced would be this mercury ion. Okay, the next question though is kind of tricky. It asks which is the better anode, and these reactions are written as reductions, and so these are for the cathode. Well, how do I get the anode? I want anode is where oxidation takes place, so I want the oxidation potential. In other words, instead of wanting these forward reactions, I want the reverse. So in other words, for an anode, the copper reaction would be opposite of this one. Okay. And because it would be opposite, I'm going to change the sign there. And I could do the same thing for this one. If I'm interested in this being an anode, I would change the sign here. So I would have -0.85, and these are volts. And that would be true for all of those, but I'm comparing these two. So which is more favorable? Well, they're both negative, but which one is least negative, closer to being positive, would be this copper. And so we have a trend that the better anode is toward the top. And I erased the other one, but it was the better cathode at the bottom. So if we really wanted a strong battery with a high voltage, we would use mercury as our cathode and the copper reaction as our anode, and that would give us the greatest possible difference. Okay, let's do another example using the table. So I have a reaction down here, and I'm wanting to know the potential for this reaction. Well, I look up on the chart, and that's not the reaction that's given. To get the potential for this reaction, I need to change the sign because this is opposite of that one. So I'm going to go to a minus 0.16. This one is the E reduction as written. I want the opposite reaction, which would be the E ox, like that. And so I would have negative. Again, for the silver, the reaction I was asked about is the opposite of this one. So I'll take this number and change the sign. Next question, which is more easily oxidized? So it's referring to these. Which of these is more easily oxidized? The more favorable reaction is more positive. Well, both of these are negative, but the copper has the smaller negative number, so it's going to be the copper. Which is the better anode? We need to remember, anode means oxidation. So this is the same question as the one before. The one that's more easily oxidized is the copper. Let's consider this chart in the forward direction first. In other words, how it is, not flipping it around. So my notes here in red have to do with that situation. So in red up here, the reason that I kind of circled these reactants is because when we start talking about what's easily reduced, we're talking about the reactants being reduced. So the lithium plus is being reduced, the sodium plus is being reduced. The lithium solid is not what's being reduced, it's the product of it. Okay, anyway, that's kind of why I circled those. And then what I said here, let's see. I'm talking about reduction here. These are all written as reduction reactions. And so I'm talking about the forward reaction. And that means that I'm using these numbers as is over here. They're negative at the top and positive at the bottom. Which is more favorable? Positive. So the reactions in the forward direction are most favorable down here. That's why I say they're most easily reduced. They have these positive numbers. Reduction is where we have what occurs at a cathode. So these at the bottom are better cathodes. They have more favorable positive reduction potentials. Okay. So if that's true, I mean, just sorting that out for the forward reactions, I know that everything is opposite for the other side. So what I'm doing over here with the purple is I'm saying, well, let's pretend like we're reversing these. And so I'm going to consider the oxidation potentials instead of reduction. And if I wanted to get those, I would change the sign. And it goes all the way down to negative 0.90. Okay. If those are the oxidation potentials, which are most favorable? These are most favorable. Okay, because they're positive up here once I flip them. Okay, and that tells you that that's what I wrote in purple, is that when this is the reactant, it is really favorable for it to be oxidized. When these are the reactants, they're not very favorable for being oxidized. Anyway, so kind of reverse relationships there. Okay, let's see another application with the table. We're given a voltaic cell, and remember that these reactions are in order, so I went ahead and wrote the half cell reactions. The zinc to the zinc ion, the copper ion to the copper solid, okay, and that's those. We might want to decide which is oxidation, reduction, anode, and cathode, so let's do that. The top one, going from 0 to plus, losing electrons, that is oxidation, and oxidation occurs at the anode. The other one is reduction, and it occurs at the cathode. Okay, so the potential of the cell, so this is the overall. In other words, this is what would read on a voltmeter if you put it between the two half cells. It is dependent on both of these potentials. Okay. The thing is, this table only has the reduction potentials. So these are all as written, and we'll have to account for that. So for the potential of the cathode, let's write in here, the potential of the cathode is the E reduction and the anode is the E oxidation. So for the cathode, we're good. These are reduction reactions, and so I would look at my copper as the one being reduced, and I would pull that number off. It's 0.34 volts. Okay. But when I go to look at my anode, so my anode is my zinc is in the wrong order. My reaction is zinc solid going to zinc ion. So what I'm going to do is take that number and change its sign. Don't want to multiply by 10. I just want to change its sign. Okay, so then I bring that down here, and this is this value right here. Okay, and then to get the overall cell potential, I add those two up. And of course it's in volts. Okay, the last thing I want to say is that be aware, how I wrote this is a little different than you see it sometimes. The way I do it is I use the one table. We all just use one table. It'll either be an oxidation table or a reduction table. And for one of the values, you pull the number straight off the table. And for the other one, you have to switch the sign before you add it up. And I like that you have to understand why you're switching that sign, that you're looking at the opposite reaction, so the sign is switched. Okay. Sometimes in classes they will give the equation like this. And when they do this, they are just pulling the numbers off the chart and then using this negative to do the flipping of the reaction for you. The problem is this chart, this particular equation goes with a reduction chart. If you had an oxidation chart, this would not work. Anyway, you do not need to know this from my class, but just something I wanted to make you aware of in case you have a class that has a different way of looking at it.